Live streaming is on.
So welcome everybody. This is the last talk for today, which is day 2 of Transform 2022. This is a digital festival conference type thing on digital geoscience in general, and everything that we're doing is as open and accessible as we can make it. So we have a whole lot of stuff happening over the course of 3 days of talks, as well as some sprints and things. The talks are all being live streamed on YouTube. And if you're watching this now, there are others available as well. Just check out the Software Underground channel. A couple of things to say before we get started with this OccamyPy tutorial. We'd like to thank curvenote.com for sponsoring or for assisting with the organization and everything of this talk. The schedule, as I say, we are at the end of day 2, or this is the last part of day 2, is on softwareunderground.org/transform. And if you are watching this live and you want to interact with our presenters, join the Software Underground Slack, which is softwareunderground.org/Slack, and have a look for the OccamyPy channel. All the details are down in the description. If you're watching this in the future, remember you can pause and rewind. You can still do that even on the live stream. So if Francesco and Ettore are going a little bit too fast, feel free to pause it and you can catch up as you will. Please share the video if you think that this is worth passing on to colleagues and friends. But for now, I'm going to hand over to Francesco Picetti and Ettore Biondi, who will be talking about OccamyPy. And over to Francesco.
Thank you, Martin, for your introduction and the assistance. Hi, everyone, and thank you for attending this tutorial. I am Francesco, and today I'm going to present this object-oriented framework that allows us to solve several inverse problems, from CT scan imaging to 3D full waveform inversion to image the Earth subsurface. Let me just start with my couple of slides. Here we go. This tutorial will be actually split in two. First, I give you a brief overview of the library with hands-on examples, where we start from quadratic problems. Then I show you how to scale to HPC using our Dask integration. And finally, I show you a practical research project about seismic imaging. The second part will be held by Ettore from Caltech. He's going to give you a deeper insight on how to conduct research with OccamyPy. In particular, he will show you Traveltime tomography applied to seismology. Finally, we present our latest work in progress, that is merging together operators and neural networks. That's quite exciting for us. And hopefully we will have some spare time for questions and answers, but feel free to reach us out on Slack. So the very first question that comes to mind is, why not using already existing libraries, such as NumPy or MATLAB? But the problem is that some of these libraries have limitations when it comes to apply them to large-scale problems. In addition, we need to define complex inverse problems. We wanted to easily save any component of an inversion if it breaks, or if we want to do a little investigations. Also, we wanted a framework that enables fast prototyping, so using existing codes without much development overhead. And finally, we needed to seamlessly scale an existing code to clusters for inverting large-scale data sets. The second question was which programming language to use. We could have used Julia or C++, but we decided to use Python to have a simple user interface that can easily interact with other programming languages, as you will see later. To define the main components of our library, we started by looking at the main objects composing an inverse problem. Let us consider two classical inverse problems, a linear and a nonlinear L2 norm problems. What are the main components? We have vectors, defining physical quantities to be retrieved or that have been measured. We also have operators, mapping vectors to different vectors linearly or non-linearly. And then we have problems that allow us to combine these two components to define an inverse problem. And finally, we have solvers that take problem objects and find a solution to that problem. Let's start with the vector class. What are the main components, methods needed within this class? We need to be able to compute the norm, some scale additions of vectors, just scaling a vector. And then we have some more algebraic computations like inner products, pointwise multiplications, and many other methods we can think about, like computing the absolute values, computing the signs, or clipped vectors values. What about the operator class? We need to have some check on the domain and the range of the vectors under analysis. Obviously, we need a forward mapping between the two domain and range space, as well as the adjoint when dealing with linear operators, of course. We also added numerical tests to debug and check operators such as the dot product test. Now, when a user needs to define new operator, what do they need to do? Simply have to define the forward and adjoint methods. Why do we need actually to introduce this concept of operators for someone that is not really into big problems? Just let's do a practical example. Suppose to have a vector as an identity matrix and build upon it. Writing the matrix down explicitly requires memory, and the application of the matrix is a matrix vector multiplication that is very expensive. On the other hand, since we know that the identity matrix does not change the vectors which is multiplied by, we can define just the two functions that copy the vectors from the domain to the range and vice versa. This can be extended to any matrix that is a linear mapping, while for nonlinear mapping we actually need just the forward. If you want to dig deeper into operators world, we just refer to John Sclairbaugh books like Basing Earth Imaging. In the case of the problem class, we really need just two main methods. One to compute the objective function value, and another for computing the gradient. Once we have defined these abstract classes for inverse problems to be solved, we actually need to implement them. In particular, we have a number of derived classes that leverages different computation engines such as NumPy or CuPy and PyTorch. Note that we adapted in-place operations in order to avoid memory consumptions. It can be tricky for pure Python users, but still we found that a good solution for our problems. This means that abstract methods, like these absolute values here, have to be overridden by NumPy, CuPy, or PyTorch functions. And if you want to implement vectors and operators that make use of another engine, such as C++, CUDA, Fortran, a new child class can be easily created. All these components can be combined to form a complicated inverse problems and can scale to be run on a HPC facility. Let's see some of these applications in the library before going to the coding part. So let's start with a simple convex L2 problem. To this end, we report the application of a least square reverse time migration that is a seismic imaging problem. Basically, we want to apply this Born modeling operator B to a reflectivity model M to get the true data. This example is of particular interest because the operators, the Born operator that is based on the wave equation, is implemented in CUDA. So the Python was actually a wrapper to these kind of vector multiplications and operations. Once we generated our data, we can easily estimate the unknown reflectivity M by solving this problem, almost to numerical precision, actually. We ran a conjugate gradient method for 2000 iterations and retrieve a pretty accurate reflectivity model by reaching the log scale objective function you see there. And also, if you can look at the retrieving percentage of the reflectivity model, we see an asymptote in this curve, highlighting the null space of the Born operator. Let's now look at L1 problems that promote sparsity in the solution. The first example is just a deblurring test solved using the iterative salt thresholding algorithm, where A represents a simple Gaussian blurring filter. We can see that a simple L2 problem cannot retrieve the original spikes, but we can see that something is there. However, when we add L1 regularization term, the retrieved images clearly shows the original spikes without any halos. In this case, we embedded the simple SciPy filter within our operator class, and we were able to easily solve this problem. How difficult is to code actually these problems? Let's see a total variation problem on GPU. We can load a NumPy file that is a shape log and phantom datasets employed in the biomedical imaging community. We create a vector torch instance on the 6th GPUs on our workstation. And then we can use a vector method, such as this scale operation, to normalize the image. Data are simulated by blurring the model with a Gaussian kernel. I would note that our library is based on algebraic notation. So D is equal to G times X. That really helps the user to focus on the mathematical formulation of the problem. We can create a gradient operator that computes both the vertical and horizontal derivatives with a second-order centered stencil in this case. And then we define the problem, that is a generalized lasso, and we impose a regularization weight of 1 over 1000. So we instantiate the SplitBregman solver, for example, asking it to store the objective function at each iteration for analysis purposes, and then we can run the solver. When the solver stops, we can inspect the solution of the problem, accessing the problem model object. And it's also possible to check the objective function components to see whether we have converged or not. Besides these linear problems, many physical inversions actually requires nonlinear algebra. Let's see a geophysical application of L2 nonlinear problems. To this end, we will show an acoustic FWI, that is the full waveform inversion. Again, all the operators have been implemented using C++ and CUDA, and then a simple Python interface have been added to them. In this case, we would like to retrieve the high resolution acoustic velocity model from observed data, starting from an initial model that is very smooth. We solve the L2 norm problem you see in the top part of the slide using an LBFGS solver for 400 iterations and retrieve a pretty accurate model, especially when compared with the true velocity map. Finally, with this short example is to show that the developed framework can also work for global optimization algorithms, such as the Markov chain Monte Carlo. In this case, we simply draw samples from a known distribution composed by the sum of two Gaussian distributed variables, so two modes. If we compare the probability density functions with the distribution of the sampled point from the MC algorithm, we can see how they resemble each other, as it should. Now, the important question is, how do we scale the existing classes to run on a cluster? Well, we can use the library called Dask, which allows to easily scale existing Python codes to multiple machines. In our case, we can do this by splitting a given vector into chunks. These pieces of vectors are then passed to various workers that run on different computer nodes. Let's consider a real case test. Let's say we have some 3D seismic survey to process. For instance, we have 4,000 time samples recorded by 2,000 receivers and generated by 35,000 sources. This vector is composed of a huge number of elements and occupies 1 terabyte of memory. Such a vector can be easily created on multiple nodes. First, we start a Dask client. Then we create a chunk template and decide the number of chunks per worker. See that this is the Dask dashboard. See that we are actually splitting the whole data set on different nodes. We are not creating copies of the data. The very same system can be employed for operator class. So we can follow a similar strategy. Let's say we have this linear modeling AM equal to D. We can split part of the operator to map portions of a vectors. And when we apply the Dask framework to the FWI problem I showed you earlier, we can obtain a quasi-linear speedup as we increase the number of nodes employed. So it really depends on the kind of problem you are going to parallelize, but it is very, very useful to have this tool in our box. So just let's move to the coding part. I shared with you on Slack a Dropbox folder with some notebook for if you want to just code along with us. Let's start from the simple quadratic problem. Our first example is just compute this following operator, so the second derivative, y equal to the second derivative of x of f of x. Let's start with the importing part. So we need NumPy and we need OccamyPy, and then I just show you here a bunch of fancy plotting functions and parameters. What we are gonna use? We're gonna use this stencil here. So for example, let's start with n equal to 5. We have 5 by 5 operator matrix D2. And we are going to fill its diagonal with this kernel here. You see the formulation. So just let's check how D2 is done. See, it is explicit vector or matrix, if you want, that deploy this simple scheme for computing the second derivative. Let's just make a more complex, more computation powerful example. How we can instantiate the vectors. In OccamyPy, we have these objects that is called vector NumPy. And we can pass to that just the NumPy array. So in this case, f is our function. We can instantiate a vector in this way. So we have passed a tuple of the shape of the vector we want to implement, and then we call a method of the vector class that is 0. Actually, this function just zero out vector values. We instantiate also the other vector. So if f is the domain vector, y is the range vector of the operator. And in this case, we can just take f and clone it. Remember, f is a vector, and our vectors have all the operation in place. So if you want to actually copy that, you need this method clone. What about the operator? For the operator, we have implemented this matrix operator that allow us to use any kind of already defined matrix, so explicit matrix. And we need to also wrap our T2 vectors there. And what we need to define also with the operator class is the domain and the range. So f is just an array, y it's another array, and d has this method get and the array that allow us to see which is the actual matrix we're gonna use. Before we set any inverse problems, let's just see the properties of the constructed operator. So we start from the dot product test with verbosity. And we see that we pass the test with numerical precision, an acceptable numerical precision. We can also have different algebraic operations like computing the eigenvalues. This is the notation for NumPy. And we can similarly do the same with OccamyPy. So in this case, we just compute the D2 power method. Oh, actually, it's not D2, it's D, sorry. With verbosity false. And we also ask to evaluate the minimum eigenvalue. Let's see if the results talk to each other. That's probably my bad here. Okay. The two methods are actually quite different. So we can also expect that we can have different results. Let's see if we add tolerance to our algorithm. Obviously, it takes a lot of time for that.
Yeah, these kind of methods, I guess, Francesco, it's to when you have an operator that takes time and you cannot apply like a simpler method. So
exactly. In this
when
case,
you don't
in
have
fact,
the explicit metrics, like when you have an operator, that's very useful to check if your matrix operator is, for instance, positive definite or something like that.
Yeah. It's an iterative algorithm, I believe.
Yeah, exactly. It applies the operator multiple times.
Indeed, if we set the tolerance to be lower, we actually reach the very same values for the maximum and the minimum eigenvalue of that operator, that matrix. So just let's move to inversion tests. Let's say that we want to define these two problems here. So phi1 and phi2. D2 in this case is actually our operator. So it's the derivative, second derivative operator. Let's say that we have observed the vector y to be equal to 1. So we just set y equal to 1 here. F is equal to 0. How to code that? In OccamyPy, we have least square problem that takes the model we want to optimize, so f clone 0, the data vector, and the operator. And we also have the least square symmetric problem. Let's say that is least square L2 problem applied for symmetric system. And again, we need to pass the model vector, the data vector, and the operator. Now we need the solver. Let's start with a simple conjugate gradient solver. That is, in OccamyPy is simple CG. And the object we need to pass to conjugate gradient or any other solver is actually the stopper. So we have implemented a basic stopper that counts the number of iteration. Let's say 2000. And then we call this line here to set some interesting attributes of the solver itself. And the same we can do that for the symmetric problem here. See that we are asking the solver to save the objective function, and in this case also to save the model. Then we run the solver, so LCG solver run. Which problem? Phi1. Verbosity true. Oh, that's a problem of this implementation, I suppose. So it's gradient function.
Can you check above? Did you pass D2 or D? Oh, you have to pass probably D.
Oh yeah, sorry, man.
Yeah, that's okay.
Thanks. Here we go. So let's see that we can also log all these inversion to some, let's say, formatted text or also a file. And the very same can be done for the symmetric solver on the second problem. Here we go. Let's plot the curves, the objective functions. And then we can also compare these two functions with the analytical solution. In this case, we can simply compute that. We need the three conditions here. And let's just code that with NumPy. And here we go, our comparison. So we can plot the problem model. So this is actually the solution that our solver has computed. We can also use the same idea to precondition the problem. So for example, if we know that T2 is available, we can use that as a preconditioner. So we can build a matrix P that is a preconditioning matrix that actually inverts that. And the problems preconditioned will be different. So it's again a least square with f clone 0 data and the operator. And we can also call the preconditioner part, that is p times p. And the same idea for the symmetric one. In this case, the preconditioner is just p. Again, we need to reset the defaults because the solver has just been run once. And then we can do the solving computation. So phi1 prec. True. See that having the preconditioner really helps the convergence. And the very same, just for comparison, for the symmetric part. As expected, we just converge to the global minimum in very few iterations, in this case just one. So see how it is actually very algebraic mathematical notations that we can use. Let's move to a different class of algorithm, that is the sparsity enforcing algorithm here, the SplitBregman algorithm. The idea is to solve this kind of problem here. So we have the objective function that is split in two terms. One is a typical data fitting problem, so it's a L2 norm. And then we have a regularizer R, that is a linear operator, that applies to the space of the solution, so the space of the model. Again, we import all the necessary modules. And this tutorial is split in three parts. We'll see the example on the recurve convolution. So let's say that we have this recurve wavelet here, and we bound that on a vector NumPy. And also we add this xinfo information that is pretty useful to embed physical information to our vectors. We load the reflectivity in the very same operation, and we need to instantiate an operator. So the convolution operator is this, actually coded like OccamyPy, comp, and d. And what it takes, x and wavelet. And the data is just vo times x. We store here some useful variables for plotting, and see our wavelet with the spectrum and the different model and data spectrum above. Let's see which is our actual model and data. So we see in the black lines we have a flattish amplitude with some spikes every now and then the convolution with the recur that is actually putting the recur wavelet on top of that. Let's start with a simple L2 problem, like the one we see before. So let's code like a least square problem in which we have the model, the data, and the operator. The solver is the conjugate gradient with the stopper that stops at 10,000 iterations. We set the defaults asking to save the objective function, and then we run the problem. It is computing the solutions using the conjugate gradient algorithm. Now it has finished, and then we can use the problem conjugate gradient model that is actually the solution that has been computed, and see how it resembles the true model, but the amplitude is not correct. So the dynamic of the reflectivity traces, for example, is not really correct. As we know that the amplitude is basically 0, but for some samples we can input sparsity in the solution. In OccamyPy, we have implemented the iterative shrinkage thresholding algorithm known as HISTA or FISTA that solves the lasso problem, that is actually the same L2 norm problem with a constraint on the sparsity of the model. Let us compute the maximum eigenvalue of the operator. That is useful if you want to apply the fast version of the algorithm. So the problem is lasso of x clone 0 data operator. Lambda value, so the regularization weights, let's say that is 1. And we can provide the operator norm to speed up the algorithm using max eigen squared. The algorithm will be HISTA. Oh. Again, we need to instantiate a basic stopper for that. And we ask to use the fast version because we have also passed the operator norm here. Again, FISTA set defaults, save object true, and then FISTA run problem FISTA false. Much more useful for this kind of problems here. You'll see that the ringing has been eliminated with respect to the conjugate gradient solution, but still the dynamic is not correct. So let's just check the SplitBregman algorithm for this kind of problem. So actually the problem, the mathematical formulation is the same, but we're gonna use another kind of problem that is the generalized lasso. Again, x clone 0 data operator. Regularizer is an identity of x, and the weights is 1. we're going to use the SplitBregman algorithm with a basic stopper of 1000 iterations, asking them to use 3 inner iteration for the application of the constraints, and the linear part is solved by 5 iterations each. So those are details of the SplitBregman algorithm, but still, just we can have the possibility to define that. We use the LSQR implementation for the linear solver. The Bregman update weight is 1. And we can also ask to use a warm start for the inner solution. Again, set default, save objective true, and then SB, run problem, SB. Let's see that the amplitude is way more correct than before. And we check also the amplitude in logarithmic scale. We see that some kind of solutions cannot be seen because of the masking part of the, let's say, the numerical solution. Let's move to another example. Well, maybe we can just, yeah. In this case, we have a 1D velocity profile that has been defined manually in this case. So we can instantiate an X vector that is vector NumPy with a shape. And then we can just access the array values as a typical NumPy array. The blurring operator in this case would be, let's say, a Gaussian filter with a sigma that is 2. And data, again, are simulated by just a multiplication. So the application.
I think you meant X, probably, G times X. On line 13 on that block. On the, yeah, that's that.
Let's see, just a moment, please.
I mean, it's
Ettore,
D
you saw
equal
that error
G.
before.
Yeah, it's I think it's G equal G times X, right? Oh, there. Up.
Well, it is not actually the expected behavior, but see that we have implemented some kind of check of the dimensionality.
No, but yeah,
So
the error I
Gaussian
think is
filter
that
will
you're
be,
calling D. You're just calling D equal G times D. D is not defined.
yeah, just asking for the domain vector and the standard deviation along the domain directions. So let's see.
Francesco, I think the error.
Oh,
Can you hear me?
Of course. I just wrote it wrongly. Sorry about that. Okay, now it is correct. So the problem was I was asking to this different vector here. Okay, so let's say the black one is the velocity profile and the blue lines is the blurred one. As we know that we have some flat regions, we can implement a first derivative as a regularization term. So first derivative of x. And the x is just d times x. Let's see the derivative here. We can apply a different stencil. Let's say that we use the forward stencil. Here we go. So these blue are the gradient samples of our model. And the gray, the problem is a generalized lasso. We use the regularization term that is d with f's equal to 0.1, for example, as b just let me copy paste here, is a SplitBregman with 200 main iterations, 3 inner iterations, 10 solver iteration. Again, is LSQR with breadth weight equal to 1. We set the defaults to also save the model, and then we run the solver. So run problem. And let's see what happens here. Here we go, perfectly reconstructed. Let's check also the convergence of our algorithm. So in this case, we can plot the objective function normalized by the first value. And then also we have this objective terms list that is actually, the blue line is the data fitting term, and the red line is the regularized weight. We can see that given this curve, we can also access the model that is being, the solution that is being found at first 2 iterations. And it resembles pretty well also the complete picture. So in this case, what I want to show you is that you can actually have the possibility to inspect different models, different solutions, different weights at each iteration to really tune your algorithm. Or we can just do that by comparing with CG and Fista, but it's not really fair. And in this case, we have also the 2D deconvolution. Let's say this one is the last example for this kind of problem. We're gonna use the shape log and phantom data. Again, we wrap it around a vector NumPy object and use this vector method, that is the scale, to normalize the value. Again, is let's say that we want to just to do a deblurring operation. So Gaussian filter of x, and we define the sigmas as 3 and 3. And data again are g times x. Let's see the model in the data. Here we go. So this is the model we want to retrieve, and these are the data image that we want to process. Again, we observe that we have flattish regions, so the total variation is a good idea. So we can just instantiate the gradient of the image. Just compute the values just for plotting them. You see, we have the horizontal and the vertical gradient here. Just for comparison, we can solve the problem with Fista. Oh, sorry, with conjugate gradient. G will be the conjugate gradient algorithm with, let's say, 1000 iteration. set defaults. CG run problem CG. Let's check the solution. It was pretty fast, and we observed that we have some ringing that is typical in this kind of problems solved with conjugate gradient. Again, we can use the total variation problem. So let's say, let me just copy and paste that. Again, generalized lasso with model, data, operator, regularized, and weight of the operator. The SplitBregman algorithm will be this one. Let's be set default save object. We can run the problem SplitBregman. We define and check the solution. And again, we also evaluate the objective function terms as we did before. While the computer is getting the solution, let me just show you that for having a plottable array, you need to call this plot method that comes with any array. That's because our implementations actually work in NumPy, CuPy, VectorTorch, and every engine has different methods to have plottable arrays. So let's see the model and the retrieved model by this total variation deblurring. And again, let's see the curves. So this is a pretty interesting approach to solve different problems using different algorithms and to compare every different characteristics of these inversions here. Of that very last example of this total variation deblurring, I want to show you another implementation of Torch. So right now we just saw vectors and operators that runs thanks to NumPy. So the vectors were built on top of NumPy, and the operator, the blurring operator, the convolution operator, were wrapping SciPy functions. The very same ideas can be done with Torch. So instead of NumPy and the arrays, we will have Torch tensors. And the operators, so the operations on top of these different vectors will be defined with different Torch functions. In this case, we still need to load the data, but we wrap it the vector torch, and we select the device. So now this vector lives on the GPU. In this case, is a Tesla. Again, the blurring is just the very same of before. So 3 and 3. D is G times X. Let's see that. Regularizer again is O gradient of X, D times X. The problem again is the generalized lasso. Let me just copy that for you with the very same weights of the regularization term. The SplitBregman will be the same of before. We need to set defaults. And then we run the solver. So problem SB. Verbose, let's say true, and the inner solver verbose, it's false. You can also access this part of the algorithm. Let's see, that is way faster than before. That's because the convolution is done on the GPU and it's parallel, and we can really parallelize that. And we can inspect as before the solution, the retrieved model. Here we go. And the objective function terms. One recently added features to our library is that see that you have this header of the log file, let's say the log system. You can add a different line, changing the name. Let's say this one is GPU TV L1 deblurring. See that? Now we can also store different information to our files. That could be useful when tackling very large inverse problems. Well, for now, what I show you is just simple operators like convolutions and gradient and derivative stuff. Actually, we were inspired into this library by PyLops. That is a very nice linear operator library for Python. And we just don't want to copy their implementation. So what we wrote is a wrapper that allow us to use PyLops operators into OccamyPy and vice versa. So just let me thank Matteo Ravasi for his work in this sense. You're gonna have a tutorial on PyLops, I think tomorrow, but it is pretty known right now as a library, so that could be also useful if you have some different research problem ongoing. So again, let's say that we have a vector NumPy. As PyLops works with SciPy and NumPy, we strongly rely on vector NumPy for this. So let's build a 3x5 vector, and we fill it with ones. We want to use a PyLops operator that is, for example, the diagonal operator with a simple diagonal vector that is a range. We can cast such operator with our operator that it comes from the PyLops interface submodule of OccamyPy. So this is from PyLops. Domain is X, range is X, and operator is the PyLops. Here we go. We have actually this D operator that is a OccamyPy operator, so we can just perform the dot test. And all the other methods that come with our implementations. At the same time, we can cast a NumPy-based OccamyPy operator to PyLops. So let's say that we have a scaling operator that would be based on X and basically multiplies by 2 the world vector. We can cast that to PyLops using two PyLops. Such operator can be used inside PyLops logic and environment. So you can use, for example, the dot test utility in this case. Let's move to a more complex example. Let's see, we wanted to resemble this example made by Matteo on CT scan imaging. So the idea is to model this equation d equal to Rm and to invert that with some kind of regularization. So this part is just copied from that tutorial, PyLops tutorial. Again, we load the NumPy arrays. In this case, we instantiate the radon to the operator, and we just check how it works. So we have the phantom model, we have the data, the simulated data, and the adjoint domain. So this is the application of the adjoint to the data. The OccamyPy equivalent will be simply vector NumPy of x. Let's say that we need vector to store the data, and theta and y. R is PyLops interface from PyLops with x, y, and I prefer to use the Hermitian of the operator itself in order to have a more consistent modeling of the equation. So this case will be R times x, and the adjoint will be R Hermitian times y. See that they are actually the same object. We can set up the total variation regularized inversion as done in PyLops. So those are the parameters that comes from PyLops. Again, the problem, total variation is a generalized lasso that will be based on x, y, the operator itself. The weights, it's lambda over mu. This is due to the different implementations we have done. PyLops and OccamyPy are quite different on that. And the regularize will be the gradient on the image space using the backward stencil. SplitBregman, again, that comes from the PyLops tutorial. So we need basic stopper for a 3 iteration. The inner iterator will be for 4 iterations. The LSQR linear solver will be run 20 times for every inner iteration, and we can use the warm start. Again, set default. And then we can run that. Let's say that we want to have some verbosity. In this case, is a little more time consuming because the operator that we are gonna use is based on NumPy or pure NumPy. So also Matteo provided that with some NumPy acceleration. I just, for this example, just tested the NumPy based one. So in the meanwhile that computes, let me talk a little bit about how that can be scaled to the powerful of OccamyPy that we believe be the nonlinear part and the Dask implementation. So let's just have this notebook run here, and let's talk a little bit about the Dask distribution. Dask is a very nice library that allows us to distribute vectors and operators, as I showed you before in the slides. What we have implemented is this Dask client. Let's see their face here. Dask client actually start a client using different HPC or workstation facilities. So we can have different clusters with SSH capability. We can have local clusters, PBS clusters, Slurm clusters, or Kubernetes clusters. So it really depends on which kind of cluster you want to work. But let's say that we use this simple client parameters dictionary and we start with a local one. Let's see. We have 4 workers. We have the worker IDs. Let's see, that is the local one. And if you have Boki installed, you can also have the dashboard. That, well, now it's not gonna work because I am connected to a remote server and I will need also to do the port forwarding. Dask vectors are the first implementation of what we call the distribution of our OccamyPy systems. We have actually 2 different methods. We can have a vector template to spread using the chunk parameters, or we can have multiple vectors to be spread to different workers. So let's start with the first one. Let's say we have a vector NumPy made of 200 by 300 samples. Chunks is a tuple. Let's say we have 3 vectors to the worker 1, 4 vectors to the worker 2, let's say 6 to the 3rd, and 2 to the 4th. Dask vector, so this vecd object, will ask for the client, this vector template, or the chunks. Let's see. Okay. This vector actually has all the methods of the normal vector class. So we can have a randomization, like say rand. We can have the norm. We can scale it up like vecd scale 10. We can clone Dask vectors. We can sum them, vecd1 plus vecd. And see that all the operators are consistent. So the operations on the vectors are consistent with each other. And we also can ask Dask to know which is the worker that has a specific instantiation of the vector itself. The other method will be to just spread different vectors to different workers. So let's say we have these vectors, vec1, we have this vector, let's say, and the last one would be like 250 and 1. Again, we can use the parameter chunks to distribute that. So Dask vector to client vectors is a list. And chunks will be consistent. So it's a tuple of 4 elements because we have 4 workers, but still we have just 3 vectors. So will be like one will be one worker will have no vectors. Let's just copy that. here and see what happens. Okay, so see that we have a list of shapes, and then we can also call all the very same operation than before. The very same idea can be applied to operators. So let's say that we want to have this vector here that has been distributed to different workers in different copies. We want to instantiate a scaling operator that will multiply that vector actually by 10. We use this implementation of Dask operator that asks for the client for the specific chunks we want to use. It asks for the operator constructor, that is the scaling, and then the operator args. Operator args are a list of the arguments of the scaling operator, so it's vec and the float value of the scale, that will be different for every vector. Here we go. Again, we can use the methods that comes with our operator. So scale.test, and we can have also this power method. Here we go. We can also try to apply this Dask operator to a vector. So let's say that we want to vec d1 equal to scale op times vec d. Here we go. Want to see the norm of the input will be vec d norm. Yeah, sure. And vec d1 will be 0. If we want to use a different vector that it will not be 0, like let's just randomize that. See? Again, we apply the very same, and we have different values here. We can also combine operator that spreads and collects local vector into Dask vector chunks and vice versa. Let's say that this is useful when the same vector is employed multiple times on different operators. We're gonna see an application of that right after. Let me check. Okay, this is the results of the PyLops and OccamyPy together. And more interesting applications I want to show you that combines all those tools I just showed you before is LS-RTM algorithm that employs devito. I am sure that some of you have heard about that. It's a particular and very useful library that allows the user to define different mathematical operation kernels to use that for different scenarios. And one of their examples are actually seismic imaging, and they have been really, really helpful on that. So let me just start with that. I provide you with this born devito file where the born operator is actually implemented using devito. So the actual computation is based on devito, and we wrap the forward and the adjoint into an OccamyPy operator. But let's just start. We have the setup dictionary. We define a little of utilities. And in that file, you can find this function that creates the model. So we have the model true, the model smooth, and the water model. We instantiate a vector NumPy on top of the velocity model of the smooth one. So that is the velocity model that we're gonna use for the Born operator itself. And again, to this vector, we add some access information. That is, this object here is a named tuple in Python that is useful to store physical information. We build the recorder acquisition geometry, and we start for a single shot. So we have a source that is placed just in the middle of our domain. We can compute the common shot gather and just plot them. So see, you have the domain, you have the recorder position on the x-axis, the time axis is on the y-axis, and it's pretty simple to see that the data. The Born operator is provided by you in that module that is Born single source. We just need to give that the model smooth, so the velocity model itself, the source position, the recorder position, and a bunch of arguments. And we can check the wave field. So here we can see that is a 2-layer velocity model that resembles one of the tutorials by devito. And on top of that, we can see the source wave field in this grayish and whitish part at time 0.5 seconds. The migration is the adjoint operation of the Born. So let's say that we take the operator and we apply that from the data. Oh yeah. I call that GGS nonlinear. GSG. Here we go. See, this is the migrated images of our reflector here in the middle of the image. For the sake of completeness, we can see also the linear data, how those data look like. So if I want to write it down in this case, the Born forward applied to an image, a reflectivity image, and that image will be computed like a vector NumPy that takes the model velocity and actually the image is the difference between the true model and the smooth model. So this is the linear data that comes from our Born operator. The interesting part is how to distribute that on Dask using different shots. In seismic surveys, you will have a number of shots, and the operator actually is quite parallelizable because you have one Born operator for each shot, and then the migrated images are just stuck together. So let's say that we have a list of sources for different source positions, so the same depth and different source x. Let me just scroll to the top. We see that we have 3 sources that will be at 100, 500, 900 meters in the domain. We instantiate Dask. And we probably need to just shut it down. This one. We have the chunk argument that will be 1, 1, 1, so 1 shot for each worker. In this case, we just used 3 workers. And the born operator is a Dask operator, actually. So it is Dask operator of what? Dask client is client. Chunks is chunks. Op constructor is the born single source. And the operator arguments will be the velocity, the source, the recorder, and the arguments that comes from these different lists. So actually we are replicating the model to different chunks. We get a source for each born we want to instantiate. We just replicate the recorder and the arguments. Let's see that. What we need is also a spread operator to spread the models to workers and stack the images back. So we have one single model that is our, actually the seismic image, and we want to spread that to different workers, compute the common shot gathers on that, and then stack them together. So we're gonna use the Dask spread operator using client chunks equal to chunk. Oh, wow. And the domain will be the model clone. Here we go. Create the common shot gather data and just plot them. Here we go. So 3 different sources, 3 different common shot gather. We can mute the direct arrival. I just provide you with a simple function to do that. Let's see how the data are muted. And finally, we can distribute them to Dask. So in this case, will be a Dask vector with client vectors are the GGS muted, and the chunks are the very same chunks. I store here some fancy label. Let's see the migration. The image will be, again, B transpose GSG. Here we go. We can see the 3 different sources here. Note the powerful of our algebraic notations here. It's just image equal to the adjoint of born from the data. We can also create some processing operators. Let's say we're gonna apply a depth gain and a Laplacian filter. And that will be simple the application of these 2 operators. So G times L times image. See that the resolutions of the image is increased. I mean, the events we want to see are clearer. And now we can go also resquares. So we can see this image here and say that the events are pretty flattish, so we can assume that the reflectors actually is flat, and we can define a total variation problem using this regularizer here. So it's a v-stack, a vertical stack, with a first derivative in the first axis, so is the x derivative in the model, that is multiplied by 10, and then we have the first derivative in the depth coordinate. In this way, we have created an unbalanced regularized term that penalize more the vertical derivatives. Again, we can instantiate a generalized lasso, model clone 0, CSG, B, regularizer is R, and F's, let's say that is 100. Problem name can be like LS-RTM TVL1. The solver is again a SplitBregman for 10 iterations, 3 inner and 3 of the solver using the LSQR. Let's say that we want to store also the objective function values. And now we solve for real. Solver, run, problem. Verbose, let's say true. Here we go. It will probably need a little bit of time for that. Well, again, we can use the very same idea to check the objective function terms here and see the problem model we're gonna use. So while the computer actually computes the solution, in this example is is quite interesting by my side, because we have wrapped an operator that has been created by another library from devito. We've wrapped that operations into our OccamyPy logic, and we can scale that to Dask, to different nodes, to different HPC facilities if we have access to one of that. And we have a pretty simple and user-friendly interface for creating different algorithms, different problems, different regularizations strategies. We can perform a study on how the regularizer weights impacts the solutions and so on. That would be our last iteration. Here we go. So these are the objective terms. And this is our image here. That is way better than before, than the simple application of the adjoint operator. Again, let's just first process that. Will be problem model. See that the reflector now is very, very bright. And we can also set up a simple conjugate gradient just for comparison. So let's say we have a least square problem. The algorithm will be a conjugate gradient for the very same iterations of the inner linear solvers that of the SplitBregman is the LSQR, so the computational time will be similar. let's have this done here. G times L times problem GG. Stop, please. And why we'll wait the solution, Ettore, if you want to just give an insight of your work.
Okay. You can hear me, right?
Move to the second part.
Yeah. Can you hear me? Francesco, can you hear me? Can you hear me, Francesco? Can you hear me, Francesco?
Ettore,
Oh, can you hear me?
are you still there?
Yes, I am.
Oh, here we are. This is the conjugate gradient solution of our imaging problem. So see that having the possibility to code different solutions, different approaches to the very same problem is actually a nice idea. And this is made thanks to Dask, that is actually very easy to use in our library.
Can you hear me now? Oh, can you hear me?
Yeah.
Okay. Maybe my headphone. Okay. I don't know why I was talking, but okay. Yeah, great job. Sorry about my microphone. Now you can hear me, right?
Yep.
Okay, perfect. Okay, let me go quickly through the Traveltime Eikonal tomography.
I don't hear Ettore, so I'm not sure if I'm not sure why. I've been hearing Francesco very clearly, but Ettore,
You cannot
anything
hear
from
me?
you, in the last while.
Oh. Can you hear me now? Martin, can you hear me? Francesco, you can hear me, right? Let me see.
Seems to be fine. I can hear you on YouTube at least. So I think feel free to go ahead, and hopefully the problem is just on my end.
Okay, perfect. Yeah, Francesco is saying, yeah, he can hear me. Okay, let's go through these then. Okay, so as you can see from, just to make sure that I'm sharing my screen. Yes, I am sharing. Okay, so I'm going to talk about a little bit about Traveltime Eikonal tomography with some example actually. So first, Francesco showed a lot about imaging and linear problems. We are going to actually try to solve some nonlinear problems using Eikonal tomography. And before we go there, basically, I want to give you a sense. We're going to record travel time as observed data, and we will try to estimate the subsurface velocities. And why do we care about these? It's because subsurface velocities, actually, they provide information about petrophysical parameters, such as the reservoir parameters, saturation, clay content, and water saturation. And that's actually some process that can be done by solving for elastic attributes. In our case, we're going to focus only on the P wave velocity of elastic waves. Also, subsurface velocities inform about fluid and gas content within magmatic chambers, and they can give you information about the melt fraction and possibly how much fluids are present in magmatic chamber, which actually informs about the force or at the pressure that we will be released in case of an eruption is occurring. Finally, also like in terms of volcanology, but in general other fields, you're going to use the velocity either to create an image, as Francesco showed, or to also interpret an image so that you can try to estimate the size of certain anomalies. What is travel time tomography? Effectively, like as I said, like the observed data vector that Francesco talked about, it's travel times, basically just how much time it takes for a source, either controlled or passive, such as an earthquake, takes to travel from the source location to the receiver locations. And inversion, it's like just tomography, basically try to estimate how the velocities that have been caused this delay between source explosion and recording the signal at this receiver location. The governing equation, it's actually like it's either the Eikonal equation that you will later see, or this path integral of the slowness vector along the ray path x. And basically like just we are connecting, basically computing the travel time from the source location to the receiver location. And this tau is the travel time. How do we do this? And as I said, like this is the travel time between the source location x and the receiver location xr. Slowness square is actually the unknown vector. XL is the ray path coordinate. And basically like here is the ray path between the receiver and the source location. We can actually discretize this equation if we fix the rays and create a linear problem. And that can be actually solved within the OccamyPy interface. And in this case, basically, as I said, like you fix the ray geometry and you discretize along the ray. And actually, like there is one way of doing this that is called straight ray tomography. You just basically, for instance, like if you have a cross well tomography, you have sources on one well and you have receiver on the other well. And if you connect each source with all the receivers with straight rays, hence the name straight ray tomography, you can actually solve and create that specific problem here, basically this G matrix that you can see here. So, and for instance, there are different applications of this, and one of them was actually proposed or shown in by A.O. Franklin et al. In 2013, where they actually tried to resolve for actually fluid migration across wells. As you can see here, you have this low velocity, and they tried to show that they are able to infer the movement of fluids in a time-lapse studies. Another thing we can do instead of fixing the rays with a straight rays, actually rays they vary a lot as function of the structure of the subsurface. We can actually pre-compute the rays and discretize them. And again, like once we fix the ray geometry, we can actually create a linear problem that can be created just by G matrix times M. What are the limitations of this straight ray tomography or fixed ray tomography? Is the fact that we fix the ray geometry, and it's highly dependent on the initial velocity model and in generalized function of the velocity model. For instance, here you can see that you have like a high velocity anomaly and a low velocity anomaly, and as you can see that actually the rays tend to go into a high velocity area and try to avoid the low velocity area. And what you can see is the fact that basically like the rays are far from being straight, and they're going to probably vary if your initial model does not contain these low velocity and high velocities anomalies. In my case, actually, in our case, we are going to solve the Eikonal equation, as you can see here, where basically you have like a velocity field that is known when you do modeling, but is unknown when you do inversion. And we try to estimate the travel time field, as you can see here. In our case, we actually use this operator-based inversion strategies to solve this problem. And we can actually do relocation. I'm not going to talk about this in this tutorial, but we're going to talk about tomography, how to do Eikonal travel time tomography in the 2D case. For instance, I'm going to show you like this example that we're going to actually reproduce. You have like f of v is actually the Eikonal operator, this operator that takes, by solving this PDE, you can actually transform a velocity field into a travel time field. And we're going to sample, of course, these travel times at a given receiver location. And the observed data are basically this observed travel time. For instance, like you can see here, few travel times for few sources, and as function of basically this receiver position here at the surface and the time that takes to arrive at this receiver location. Let's say that we want to minimize this problem. We're going to solve this problem actually with LBFGS, which is a nonlinear optimization method present in our optimization library. You can see that this is the initial model. We basically here we only know an initial velocity model, and we observe some data. We run the inversion, and we obtain that there was something like some anomaly here. And if I show you the true velocity, you can see that actually like we retrieve a pretty accurate velocity model. Now let's try to reproduce this example. I'm going to go and show you here on this Traveltime Eikonal tomography. So here again, like as Francesco showed, we import some library, our OccamyPy, and we're going to import this Eikonal 2D that is part of the library, SK, which is actually like where you have like those operators. And if I have time, I will show you a little bit inside this model or this module. Let's start to define the spacing of the spatial grid. In this case, we're going to use basically 100 meters or 0.1 kilometers. We're going to instantiate a model that is around 201 samples in X and 101 in Z. Then we are going to actually instantiate or create a linear space by just typing these, and X minus 1, basically just to get like a good axis for plotting, and in general for placing the receiver and source at the right spot. And again, like Z minus 1 times Z. Let's create actually our OccamyPy vector. And in this case, I'm going to just use similar notation that Francesco showed over and again. Basically, like we have an x times nz vector, and we put actually some axis information, like the first axis, or basically the slow axis is the x direction, and the fast axis is the z direction. In this case, we're going to use a simple velocity field. I think one of the beauty of OccamyPy is the fact that we don't even know that this is a vector NumPy or whatever. We could have used some other kind of engine. In this case, we are using the vector NumPy, but I'm accessing there. It's the element of this vector by very simple close notation as NumPy. So in this case, we're going to use this simple velocity field, as you can see here, basically just constant velocity of 1, and we add some gradient in the z direction. And we're going to visualize that very soon. Let's put some basically like source location. In this case, we're going to actually use 3 sources, and we are going to provide here the actual location. And you can see we're going to put basically at 0x and at the last index of the grade. Then we're going to get another one in the middle, actually. So we do this thing, and then we again like nz minus 1. Okay. And finally, the last source is going to be placed at the very end of the x location. Now, the receiver location actually are going to be spread across the surface. So here we have like sources at the bottom, and here we have receiver at the top at every grid point in X at the 0 grid location. Let's instantiate also the observed data vector. Again, like very similar notation as Francesco in a sense here. Vector NumPy, source position. Here, basically the vector of data is as big as the number of sources times the number of receivers, right? And the axis information is just to give a sense of the axis information of the data. In this case, we have basically like the source location. It's like actually source ID, and the vector. We can actually use the axis infos from the velocity. And let's use the next step is actually to instantiate this operator, the Eikonal nonlinear operator. This case, we get the Eikonal 2D, whose input are like the velocity, the data vector, source position, receiver position. And notice that because we use actually the axis information, we can provide, or we access those information such as the grid spacing and the size of the velocity from the axis info. So it's like we get like a very, very tidy interface. So we can get these. And again, like we can call the forward operator. The velocity is the input, and the travel time data is the output. We run this, and we get this. We basically run, it's pretty fast, as you can see. We can plot some data. This case is like receiver position, and these are the three sources in that velocity model. Also, we can actually like create the adjoint, or basically like the linearized operator. In this case, we have to call Eikonal lin 2D. So this one is the Jacobian, if you are familiar with nonlinear inversion, the Jacobian of this operator here. Okay, that is going to be very useful for running like a nonlinear inversion. Again, like the input is very similar: travel time, data, source position, and receiver positions. And again, like as Francesco showed, we can actually do the dot product test with some verbosity, run this, and we can check whether the operator provides accurate and correct. And you can see actually, like, because we're using double precision numbers for doing the computation, we get a relative error of 10 to the minus 16. Okay, you can see that we're going to actually do an inversion now. We actually just do some modeling. We check that the operators are correct. By the way, it's really important. Like this dot product test, when you code the linear operators, is very, very important. It's fundamental because it can save you a lot of debugging, especially when you work with operators, such as this one that is pretty complicated. So again, we can try to do some inversion. In this case, we can actually, again, create some velocity vector, and V0 stands for the background or the initial. Again, we can just use the same exact notation as before. So this is the velocity field that we used, and we will see it very soon here. And in this case, we're going to place a Gaussian anomaly. And to do this is very similar. We create this Gaussian anomaly. This is like a pretty standard way of creating 2D Gaussian anomalies, but this can be done in 3D easily. In this case, we use OccamyPy clone. Perhaps we can even use 0, just in case. 0. But with 0. And then we can actually just add the Gaussian anomaly here, and we scale by 0.5. Oh. Okay, let's visualize the background velocity model. Notice that in this case, we are using the seismological notation for velocity colors. Red means low, and blue means high. In another notebook, and if time permits, I'm going to show you actually the usual notation for seismic exploration. Let's also plot the true velocity, which is actually, I made a small mistake. It shouldn't have been 0. It should be this. Here we go. And you can actually see, we can actually open these two just for reference. And I can show you that basically like it's the same velocity model without the anomaly. Okay, let's try to do some inversion with this. And to do this, again, like we can actually do, again, probably just copy the data if we still have them. Actually, let's copy here. So very, very similar syntax again. ID. Notice that in this case, we're going to use actually They can run 10 sources placed on the bottom of the domain, and we are going to use receiver at the top of the domain as before. And again, like this case, we're going to create our nonlinear operator first. This is the nonlinear operator. And again, here, the Jacobian of the nonlinear operators. One thing that we are doing here is to save computation is the fact that actually, like, we're going to take some component that is the travel time maps from the nonlinear operator, which is computed when we do the nonlinear modeling. And we are going to actually use that to inform the travel time map within the linear operator. This is very important because it's going to save some computational time. Travel time data vector, we clone it, we create some data observed. Again, like we use the true velocity and we generate observed data. As you can see, it's a very small task and it runs very fast. Let's visualize a little bit the travel time. You can see that here we have receiver location at the surface and travel time. As you can see, like, you have a clear kink in this curve that is due to the presence of that anomaly. Okay, so this one is a nonlinear problem, as I said. So we need to solve it with a nonlinear solver. And but the syntax is very similar as before. So we have OccamyPy, we call the FGS, we call our basic stopper. Let's say for and iter equal 25 iteration. To help a little bit the inversion, actually, we're going to use a Gaussian filter because it's to kind of mitigate some of the artifacts, if you may. And to do this, we can actually easily call this Gaussian filter. Then we have basically like this velocity vector, which is input, and the Gaussian smoothing variable. And in contrast, as Francesco, in a sense, that showed linear problems, in this case, we're actually going to use nonlinear operators. And to do this, we basically can call this nonlinear operator, whose input is actually like this Eikonal operator, which is the nonlinear mapping operator from the velocity to the data space or the travel time space. And it's Jacobian, which is this guy. The beauty of OccamyPy is like so high level that we can say our Jacobian is not just the Jacobian of this nonlinear. We can actually concatenate already some kind of matrix or some operator that cleans up the gradients, for instance, such as these, or if you may preconditioner, some people like to call it. The last part is actually we need to know where to compute the nonlinear operator Jacobian. Basically, like the Jacobian matrix of a nonlinear function depends on where you compute this function. And to do this, basically, like OccamyPy relies on this third argument, which is basically a function or a method within the linear Jacobian that tells the engine, the OccamyPy engine, where to compute the Jacobian matrix. Very similarly as before, we can actually use like a similar syntax, but in this case, we're going to use a nonlinear least square problem, just exactly what I showed you before in the presentation. We're going to put some bounds, as you can see here, maximum velocity of 1, minimum velocity of 1, and maximum velocity of 2.5. And we use the nonlinear operator. And again, like it's as simple as before. Once we run this, we can call this nonlinear problem solver. We can pass our nonlinear problem verbose for true. And let's see, and we can run this. It's going to take a little bit of time, but not a lot. And as this runs, we can actually perhaps look slightly at this operator here. This is actually like what we use to wrap some function into an operator. So this one, it's a good way of, it's a good how can I say, introduction to get a sense of how to write your own operator. And in this case, actually, for instance, like this class Eikonal TT2D wraps actually like a pretty efficient travel time modeling code that is called Eikonal, and it does in a very efficient way. So you can see that actually, like, since we know already like there is a package to do this travel time modeling, we just wrap it into our interface, and you see that it doesn't take very long time to do it. And it can be parallelized. There are like a bunch of things to do. All these other functions are to compute the Jacobian. So let's go back. You run the 25 iteration, as you can see. And again, like, let's open up this image for comparison. You can already see that there's something there. This is the initial model, inverted model, true model. So you can see that actually, like, we retrieve a pretty decent model. Okay, and that's for this simple example. So I'm going to try to finish in 10 minutes or so. And I want to show you at least the Crosswell tomography case, which is a little bit more maybe interesting. So in this case, we're going to use, again, like Eikonal tomography. And here, like, some description. Again, same exact importing. Here we are going to use actually the Marmouzy model, some loading. We're going to actually use just a small portion of the Marmouzy model with this sample, because it's like this one, it was sampled at 10-meter spacing. We're going to use 40. And again, like, very similar as before, and just extend for plotting. And in this case, I'm going to show you, actually, we instantiate our geometry. Just to give you a sense, this is the geometry. Source is in the middle, receiver on the sides. And we're going to try to do Eikonal tomography, Crosswell Eikonal tomography in this domain and in the true model. So again, like, we can actually, again, try to do the same thing as before. So we instantiate our vector, observed data vector. We can compute our Eikonal data. And again, we can just do this for the forward modeling operator for the travel time to be true and the obs. See, it's pretty fast. We can visualize the travel time, or basically the travel time map for the source at the bottom, or like even we can actually, even like in the middle, for instance, you can see how it changes. You can see that actually we are storing the travel time maps inside the object, as you can see here, as an array. We can actually plot some data. Since it's Crosswell, we have this. This is one side of the receiver. This is the other side, as you can see, for just 3 sources. So now, for doing the initial model, we're going to, again, like, use a Gaussian filter. In this case, we can just use, again, the OccamyPy syntax. And BB true. Again, like, it's as simple as Francesco showed. And do BB true. Here we go. And we can plot the initial model. Again, like, let's open up this for reference. So for comparison. And again, let's try to basically, like, solve this problem, or basically, like, just let's try to first instantiate our Eikonal operator, the linearize, or the Jacobian of that nonlinear operator. And in this case, again, like, very, very similar as before, right? So we create our nonlinear operator, or nonlinear solver, a new Gaussian filter, which has slightly different Gaussian blurring filter, and then again, our nonlinear operator and our nonlinear problem. Same exact trick, run. It's going to take a little bit longer. We're going to run actually 20 iterations. This one is a little bit bigger problem with more sources, but hopefully, like, it's not going to run too slow. And as this run, actually, I can show you that this kind of operator and this library has been used actually to solve a pretty relevant topic or problem in the Long Valley caldera, which is kind of a super volcano located in California. And this is a work that I've done with many people here at Caltech, and we presented this work last week at the Seismological Society of America meeting. Just to give you a sense, actually, like, this is kind of one of the recording that we use to know kind of the energy of an earthquake. And we use actually machine learning. One of my colleagues, Wei Chan Zhu, work on this method. Basically, we use machine learning to obtain the travel time peaks that are shown by these red dots and the blue dots for the S wave. Just to give you a sense of how powerful this method and this library can be if used properly, this is kind of the view, the satellite view of this area. These are the receivers, if you may. And this is kind of a volcanic lake. This is the caldera of the volcano. And this is a depth size of the initial model. And if you use basically OccamyPy to solve this problem, you can actually obtain a pretty high resolution model. And actually, like, one of the incredible things we saw is the fact that there is like a pretty strong low velocity anomaly around this volcanic lake. And actually, even if we do this for VP and VS, again, same exact area. This is the contour of Mono Lake and contour of the caldera. We run this inversion. We obtain some anomalies. And one incredible thing that we noticed is the fact that there are some anomalies that actually align pretty well with some volcanic flows or eruption that have been seen from the surface from geological surveys. And of course, we can extract like profiles. And this is the initial model for VP and VS. This is the inverted one. And you can see that actually, like in the Long Valley caldera, we obtain a very detail of the hydrothermal system, and also like this anomaly in the Mono Lake. So hopefully our inversion is almost done. In fact, it is. Let's look at our inverted model. So initial, inverted, true. And you can see that actually, like, for instance, like if you focus on this anomaly was actually underestimated, and now the velocity is pretty well accurate. And the same goes with these other anomalies, where you can see that before they were very low in absolute value, and now actually they're closer to the truth. So showing that actually, like, this method can work when everything is set up properly. And I guess with that, I can actually stop and maybe let Francesco draw some conclusions. If Francesco is still online.
Yeah. Here I am. Well, thank you, Ettore, for wrapping me up, and I am sorry for the time I consumed before.
Okay.
Yeah, to draw the conclusion, well, this project is actually born for our research, so it is really committed to open science and geophysical community, let's say, but we want to just move and code all the parts in order to be scalable and make them usable for other users cases and other scenarios, let's say. We have a lot of work going on right now. We just coded different examples of the very same scheme using also the automatic differentiation based on torch. You have just a little application of the vector torch we have implemented, but we also have some stuff going on in merging together linear operators and automatic differentiation that can be very useful to close the gap between, let's say, traditional inverse problems and machine learning stuff. And we will really appreciate your comments, and please reach us out on GitHub and check that. And if you want also to collaborate, just reach out, and we are pretty happy to give us the opportunity to expand our knowledge in a sense. Let me just thank once more Matt and Martin for having invited us and the help through this tutorial. And thank you for watching.
Yeah, thank you.
Yeah,
Thank you very much.
thank you very much. I thought that was really interesting. You guys have got a really nice, clean API. It'll be fascinating to see what the wider community does with this. If you haven't yet, there might still be a space for a lightning talk. If you can pitch this in 5 minutes to people, that might be fun as well. But yeah, thank you very much, Ettore. Thank you very much, Francesco. There are still some other things happening for tomorrow. So this was the last talk for today, but there will be some tomorrow. Check out softwareunderground.com/transform to see the schedule. This video will remain up, so please do share it if people are, if you know of people who would be interested in it. Thanks again to CurveNote, and otherwise we will see you for another video short, or for another tutorial starting tomorrow at 8 a.m. UTC. So have a good one.